So I've decided that I'd like to take a stab at working through one of the situations that we're seeing in lecture, and I guess some of us are not understanding. So this is going to be the derivation of the expression for the electric field of a ring of charge. So I know you guys have done probably the line of charge. I think. Oh wait, did I say ring? Oh whoops, I meant the disk. Good God. So you guys have done the line in the ring. We are going to do the disk, or I'm going to try to do the disk because I have no life and this is what I do. So we're looking at a ring of total radius r, right, composed of very small concentric rings of radius dr, or that little infinitesimal, whatever they call in the book, the infinitely small radii rings, and composed of charges dq, right? And so in this case, we're always looking to express the charge q in terms of a geometric quantity. So say you have an area charge density eta, right, where eta is just the dq over the da, or since it's uniform, it could just also be the total charge over the total area. So in order to get the little dq's, we just multiply the da's by the eta. And so that's how we're going to sum things up. So let's think about two charges on radially opposite sides of the ring, right? So if we have this bottom charge, let's say it's positive, and another positive charge, probably about up here. When you evaluate the electric field on the axis of the ring, i.e. at, with no, you're not up or down, you're just on the axis at like z equals 0. I mean, like y equals 0, all along the z-axis. You're going to end up with electric field vectors that look something like this, right? So the bottom charge is going to contribute this electric field vector, right? The top charge is going to contribute this electric field vector. And we see that the charges are identical. The charges are identical, and they're at identical radial distances from this point. So the y components of these vectors are going to be the same, but they're equal and opposite. So they add to 0, right? So because of that, we're only going to look at the z component of the electric field from one charge, right? So if we look at this here, right? So this is as if we were looking at the ring from the side. So this is the r, the distance from the middle or the axis of the ring up to the disk we're trying to integrate through, and then this is the distance z from the ring along the axis. So we're able to see that. Let's see. This angle theta. How was I going to explain this? This angle theta equals the angle theta that the net electric field of the top charge, this vector. So these angles are the same, right? But we only want the z component of that total electric field, right? And so that DEZ, or the z component, is just equal to the total field, right, times the cosine of the angle. Right, so that's what we're going to use when we're finding the electric field along the axis, because we know that when we take everything and add it up, we're only going to end up with something along this axis or along this line. So that's what the net electric field is going to look like. So we always want to start with Coulomb's law, right? So our little infinitely small electric field is going to be equal to our dq. Well, 1 over 4 pi epsilon naught I like to use. You guys might like to use k, but I got in the habit of using this one, times dq over, and I'm going to call it m squared, which is our radial distance from this point. Each charge is some radial distance away from this point. What was I going to say? Oh, and times cosine theta, like I said. So now I'm just going to go ahead and make all the substitutions. So first off, we have that dq equals e to dA, right? Let's just throw that in right now. We'll deal with it later. This m squared that we have. So say this radial distance, or this is the position of the top charge at the top of the ring, right? So the top charge, if we look at the ring from the side, it's r above its this little origin here, right? So the distance from this top charge to the point where we're trying to find the electric field is, you know, this Pythagorean sum of the r and the z, right? Which is just r squared plus z squared. So we have the square root of r squared plus z squared all squared, right? Times, okay. Times, and then it's cosine theta. Well, cosine, we know our SOHCAHTOA or whatever. That's just adjacent over hypotenuse, right? So we're talking about this angle theta because this angle theta right here matches this angle that we're using to find the z component of this net electric field. Because they're vertical angles and we love geometry. So adjacent over hypotenuse is just z, the adjacent over r, right? So that's what our cosine theta is going to come out to be. It is z z over r squared, over the square root of r squared plus z squared, adjacent over hypotenuse. All right, I promise, guys, that I passed the 10th grade. Please, no judgment or laughter. It has been a long day, and I am just... All right, so now I'm going to simplify things. So we have this e to dA, which we're going to deal with in the next step, because I don't want to overwhelm people with the extra details. Times, the only thing we're going to have on this numerator is z, right? Left over. Times z. And then this, the square root of r squared plus z squared, squared is just r squared plus z squared, times the square root of r squared plus z squared to the first power, which, you know, TLDR comes out to be r squared plus z squared to the 3/2. Oh, so pretty. And then, so let's deal with this dA element. So if we took this ring and let's say we cut it, kind of like you cut, I cannot think of an object that, so what if you had like a circle of yarn, you cut it and you laid it out and made it form a rectangle. When we cut this, this little circle of ring and make it a rectangle, we end up with this. So this length here is the part that was strung around in a circle, right? So it's going to have radius, or it's going to be the circumference of the circle, right? So we have 2 pi r on this part, and then this little sliver here is just this little dr part, right? And so now we know the area of a rectangle, just length times width, fun stuff. So then this dA ends up being length times width, which ends up being 2 pi r dr. Fun stuff. And now we're going to simplify this. So we have eta, again, our charge density, times 2 pi r dr over 4 pi epsilon naught times our z over the r squared plus z squared. I'm not paying attention to what I'm doing. I'm going to simplify this even further. So our pi's cancel out. Goodbye, fam. And then the 2 and the 4 becomes a 1/2, so that's just a 2 in the denominator. I'm going to keep everything else. So I'm going to move some things around. I'm going to put it this way. So we have eta times z times r dr, and this is over 2, over r squared plus z squared to the 3/2. And so now we're just about ready to integrate and make sure that I have not done anything stupid. Where are my notes? Yeah, I think we're good. Oh, I forgot the epsilon naught. Jesus. Got to carry over all the terms. So we're just about ready to integrate. So what are our bounds of integration? Well, we're just going to go from the middle of the ring to the outer radius, right? So when we form our integral, bounds are from r to 0. Big R to 0, not little r. Little r is just the, just ignore what I'm doing. So we have the integral all this crap. R squared plus C squared to the 3/2. So let's pull out some things, because we have a lot of crap here that we don't really need all of. Let's note that this variable z is a constant, right? So as we integrate up the ring, so this is a dr that's even smaller than our little r. From dr to dr to dr to dr to dr to dr, we are not changing this distance at all. Z is a constant, so we don't have to put it in the integrand. So we pull all the constants out. We know that eta is a constant, and epsilon naught is just the permittivity of free space. Fun stuff. And so now we have the integral of r dr over r squared plus z squared to the 3/2. I hope to God I have enough room to do this on this page. All right. So now this, luckily for us, this is a very simple u substitution integral. We're just going to let u equal r squared plus z squared. Du then is just 2r dr. So then we're able to see that this r dr part of the integral is just du over 2. So that transforms. So now, okay, so we transformed everything in the integral. Let's transform our bounds, right? So this r and 0 correspond to what the values that r can attain, right? So when r equals 0, then u equals z squared. When r equals r, or capital R, u equals, oh God, I'm going to run out of space, aren't I? R squared plus z squared. All right, so here's where things are going to get small. So now transforming all this crap. Transform the things being integrated and the bounds. So we're going from r squared plus z squared to z squared. And we're doing the integral of, this should be du over 2 times, why am I doing this so bad? All right. Why did I not leave room for, all right, times 1 over u to the 3/2. All right, this is not how you should ever write your integrals. I'm just going to rewrite this again so it looks pretty. R squared plus z squared, c squared. So this is 1 over 2 times u to the 3/2. Yes, du. Right. And so the integral of u to the 3/2 is just going to come out to be, I think I'm going to make it, guys. Like, I don't think I'm going to have to flip pages. It's going to be, so we still have this 1/2. It's going to end up being u to the negative 1/2 divided by negative 1/2. So when you just divide by negative 1/2, you just get the negative 2. And the bounds were from r squared plus z squared to z squared. Oh, this is not going to make it. All right, so TLDR, when you plug these things in, so these twos just cancel, right? We see this. And we're getting that we get negative what on God's green earth am I doing? Okay. So we end up with 1 over the square root of r squared plus z squared minus 1 over the square root of z squared. Which, all right, this is where I'm going to pull out some witchcraft. Which comes out to be So I'm going to factor this negative in. So that's all this negative is going to do is just reverse the sign of these two terms. We're still going to have this eta times z over 2 epsilon naught times, oh crap. So this is supposed to be the square root of 1 over z squared, right? So this square root of 1 over z squared is not going to be positive. I'm going to write it first. But we know that the square root of z squared is just 1 over z, right? So bam. So I flip this sign. This is now positive. And just simplify the square root. All right, so now this term is going to be negative, and nothing's going to happen to it. It's just going to stay the same. Minus 1 over the square root of r squared plus c squared. So this simplifies to, again, we have the eta over 2 epsilon naught times, well, this z here just cancels with this z. We get 1. And then I'm going to multiply this z through here, just distribute it through. We get z over the square root of r squared plus z squared. All right, so this is our raw result. I have run out of paper, but there's more that we need to talk about with this. So let's think about what happens in the limit that z gets real big, right? So if you have, so z is like 1,000,000, right? But r is like 2. You know, so this radius of our thing is like 2. Oh god, I hope no one saw my feet. This radius of this thing is like 2, and then let's say this z, this distance from the disk is really large. So z squared, 1,000,000 squared plus 2 squared is pretty much 1,000,000 squared, right? So okay, let's go ahead and see if I can simplify this. All right, we're gonna move this. Hold on. So from here we have eta over 2 epsilon naught times 1 minus, so we have z here, which again is really large, and then this r squared plus z squared is essentially just z squared. So again, we have the situation where we have the square root of z squared. Let's see. What have I done? I think I've done something wrong. No, I have not. I feel like I have. Well, the point is that when z squared gets really big, this is supposed to vanish. Yes. I feel like that's what's supposed to happen. Yes, so this is supposed to vanish. And you end up with a field that's just constant. So that this becomes 0. Goodness. What on earth have I done? Anyway, so that term's supposed to vanish, and you should end up with a field that is just constant. And so this is the field of a parallel plate capacitor. Just one plate of a parallel plate capacitor. When you get 2 plates, they'll each have a field of this, and the eta over 2 epsilon naughts will just add up to just eta over epsilon naught. But that was the idea. So that's the video. This seems to be kind of a disaster. I'm going to figure out what I did wrong.